All right, today we're going right back to the fundamentals with a core concepts revision for civil engineering. We're going to do a quick but deep dive into the principles that let us build, well, everything around us, from towering skyscrapers to massive dams. So whether you're a student cramming for an exam or you're just curious about the science that literally holds our world together, you're in the right place. You ever just look at a huge bridge or a skyscraper and wonder, how? How does that thing just stand there? Well, the answer isn't magic. Not at all. It's actually a set of core scientific principles that every single civil engineer has to master. And today, we're going to walk through the most important ones. So we've broken this down into 4 key areas. First up, we'll learn what I like to call the language of force, looking at stress and strain. Then we'll dive into the principles of flow with fluid mechanics. After that, we're going to uncover the secrets hidden right in the soil with geotechnical engineering. And finally, we'll see how all these ideas come together in the logic of structures. Let's get into it. Okay, so first things first. Before we can even think about building anything, we have to understand how the materials themselves are going to behave. How do they respond to being pushed and pulled and twisted? We basically need to learn how they speak the language of force. So, what is stress, really? Well, imagine a heavy truck driving over a big steel bridge beam. That beam isn't just sitting there passively taking the weight. No, its internal fibers are actively fighting back, resisting that force. Stress is just the measure of that internal fight, spread out across the entire area of the material. And calculating it is, believe it or not, pretty straightforward. Nominal stress is simply the external force, we call that the load, or P, divided by the original cross-sectional area of the material, or A. And this simple little ratio, it's incredibly powerful. It lets engineers compare how different materials and different shapes perform, and it's how they figure out if a part is strong enough for the job. This brings us to a really crucial property of materials. When you're in the elastic range, a material is just like a rubber band. You can stretch it, and it snaps right back. But if you push it too far, you cross a line into the plastic range. And that's more like a paperclip. You bend it, and it stays bent, permanently. For an engineer, that line between the two, the elastic limit, is one of the most important numbers there is, because crossing it means permanent damage, and that is the first step toward failure. Okay, so we've covered the internal forces happening inside solid materials. But what about the external forces? The ones from things that flow, like water rushing through a pipe or wind pushing against a skyscraper. To get a handle on those, we need to jump into the world of fluid mechanics. Whoa, okay. Don't let this equation scare you. This is Bernoulli's equation, and at its heart, it's really just about the conservation of energy, but for a moving fluid. It connects a fluid's pressure, its velocity, and its height at any 2 points. Put simply, it tells us there's a trade-off. If a fluid speeds up, its pressure has to go down, and vice versa, as long as the height is the same. Oh, and that little HL at the end? That's our dose of reality. It accounts for all the energy lost to friction. But, and this is a big but, the classic simplified version of that principle only works perfectly under a very specific set of ideal conditions. For that simple version to work, the fluid has to have 0 viscosity, no stickiness, the flow has to be perfectly steady and not turbulent, and it has to be incompressible. In the real world, of course, none of these are ever perfectly true, so engineers have to know when this ideal model is a good enough guess and when they need to break out the more complex math. So you might be asking, okay, cool principle, but where is it used? Well, the Venturimeter is a perfect real-world example. It's a simple device used to measure how fast a fluid is flowing. By forcing the fluid through a narrow section, a throat, it deliberately makes it speed up. And what did we just learn? When velocity goes up, pressure goes down. So this creates a predictable drop in pressure that we can easily measure. By checking that pressure difference, engineers can calculate the exact rate of flow. It's just a really elegant way of turning a physical principle into a practical tool. We've covered materials, we've covered fluids. Now, let's get down to earth. Literally, we're talking about the most important element of all, the ground right beneath our feet. Every single structure ultimately rests on soil, and understanding how it behaves, that's the job of geotechnical engineering. Okay, it is absolutely crucial to understand the difference between 2 terms that people mix up all the time, compaction and consolidation. Compaction is all about squeezing air out from between soil particles. It's a fast, mechanical process, like when you see a heavy roller on a construction site. Consolidation, on the other hand, is about squeezing water out. And this is a very, very slow process that can take months or even years, as it happens naturally under the huge, sustained weight of a building. So the key things, remember, compaction is fast fast and removes air. Consolidation is slow and removes water. And getting that compaction right means you have to use the right tool for the job. For sticky, clayey soils, you need something called a sheepsfoot roller, which kind of kneads the soil to force the air out. But for granular soils like sand, a vibratory roller is way more effective. It uses high-frequency vibrations to literally shake the sand particles into a denser, more stable arrangement. All right, let's bring it all together now. We've looked at material properties, external forces, and the foundation itself. Now let's see how all these principles combine in one of the most fundamental structural elements out there, the beam. It seems so simple, doesn't it? Just a horizontal plank supported at both ends. But how does it actually work? How does it fight back against the forces that are trying to bend it and snap it in half? Well, the answer lies back in those internal stresses we talked about at the beginning. One of the key players here is something called shear stress. The best way to picture it is to imagine the beam is a thick deck of cards. If you press down in the middle of that deck, the cards all want to slide past each other, right? Well, shear stress is the internal invisible glue that resists that sliding action, keeping all the layers of the beam working together as one solid piece. And here's something that might surprise you about shear stress. You'd probably guess the stress is highest at the top and bottom surfaces, where all the bending seems to be happening. But for a solid circular section, the maximum shear stress actually happens right in the middle, at the center, the neutral axis. So while the top and bottom are busy stretching and compressing, that internal sliding action is most intense right at the core. That peak stress is about a third higher than the average, a detail that is absolutely vital for engineers to factor into their designs. So there you have it, the 4 interconnected pillars of civil engineering. It all starts with understanding how materials fight back against forces. Then you have to account for the forces from fluids like wind and water. You have to make sure you have a solid foundation in the soil. And finally, you combine all of that knowledge into a logical, safe, and efficient structural design. And that brings us to one last thought. These principles have served us incredibly well for centuries. But now, as we're developing things like self-healing concrete, ultralight composites, and we're facing brand new environmental challenges, which of these fundamental rules do you think will be the first one we'll need to rethink? It's a fascinating question, and one for the next generation of engineers to solve. Thanks for digging into this with me.